Welcome back to Demystify Sci. I'm Shiloh.
I'm Anastasia.
We are back with a third take on how atoms talk to one another. And what I mean by that is light, of course. And if you've been following the show for a while, you know that we are really curious about the transactional interpretation of quantum mechanics, which was first brought to our attention by Carver and Mead. It turns out he picked up the idea from a dude named John Cramer, who we recently had on the show. And there's a third voice in this mix, which is Ruth Kastner. And she's a physicist and philosopher who has a very separate and unique take on the transactional idea, which is really just looking at light, not as this photon being shot off into the dark, but as a process by which two atoms come into energetic equilibrium. And that is really exciting because it takes a lot of the spookiness out of quantum mechanics, and we can start to actually get our hands on paradoxes like the double slit experiment and everything in between, and quantum entanglement, all of this bizarre stuff that doesn't really fit into our classical understanding of mechanics. And so today's conversation really toes the line about what is mechanics? What is that in respect to a mechanism? Are mechanisms and mechanics the same thing? Why have we abandoned mechanics? Have we abandoned mechanics? These are really important topics when we approach something like physics, because does physics just study everything, or does it study something specifically? And we tend to think it's the latter, right? That it should actually be providing mechanical explanations for phenomena. But quantum mechanics, of course, threw a wrench in the gears of that process, and we're unpacking that today with Ruth.
And ultimately, the conversation is about this question of what an explanation looks like. And it's something that we've touched upon in other episodes and something that we talk about all the time when we're recording solo conversations. But fundamentally, science appears to have the obligation of providing an explanation. And a lot of physics appears to come at this from the mathematical standpoint, where you need to come up with some kind of equation that can describe your system well enough for you to be able to make predictions about it. And it's actually possible to come up with that mathematical description in an ad hoc way, where you look at the surface level of your outcome, figure out some equation that describes it well enough, and then you're able to move on and do something else without ever asking the question of, okay, where does that math come from? And that's really what we're circling around today, which is, if we have the math, that's great, the math works, where does it come from?
It's really funny, too, because this interpretive level seems to be orphaned to some extent. Does it belong in physics? Does it belong in philosophy? And you'll very quickly find that when you start diving down this rabbit hole, you'll find that neither one of those departments really wants it. You know, the philosophers will say, this is a physics problem. Physicists will say, this is a philosophy problem. And so that's really exciting because it represents something that's actually really quite important, but it isn't getting the attention it deserves. And we're obsessed with it.
And if you like the things that we are obsessed with, consider coming over to patreon.com/demystifysci and supporting us for a couple dollars a month. It is absolutely instrumental for our survival, so we don't have to plaster ads all over this program, and so that we can hire folks who can help us with booking, we can upgrade our equipment, and spend more of our time doing what we do best, which is researching the topics that we explore on the show so that we can have good conversations with our guests.
And how cool is that? The artwork would be supported directly by the people who enjoy it, as opposed to through some weird capitalist goop that you have to sling around in order to fund what you actually want to be doing. So support the movement. Come over to patreon.com. We have the super thanks enabled on YouTube, so you can just give one-off donations. We got a donation link down below. We got t-shirts for sale, which we're not really making money on, but you can share the Demystify Sci idea with people by rocking a t-shirt. Otherwise, just leave a comment. Get involved in the discussion. Tell us who we should be talking to next. Tell us what you think. Tell us what idiots we are. Whatever. Just come and join in the discussion.
Yeah, one last point before we move on to the episode. There's actually an opportunity for us to get together in person. One of our previous guests, Gopi Vijaya, who's working on an alternative framework for science that allows us to really deeply consider theories that are either contradictory or antithetical to the ones that we have right now, is hosting a conference in the Bay Area in Menlo Park on October 31st through November 2nd. It's called the Renewal of Science Conference. we will probably be there, and so you should absolutely check it out. He has an amazing list of speakers, including Simon Schack. So if you're into the Tychos model and you want to see Simon in person and you want to ask him all the burning questions that you have, consider coming to the Renewal of Science Conference.
All right, guys, enjoy this conversation. Tell me what you think down below, and I'll see you next time.
The scientific revolution starts now.
Let us see in the dark.
I mean, I'm really, really excited that we have this opportunity to talk to you. Just from a very personal background, I might just say that we've been fascinated by the idea that atoms are talking to each other in some way, particularly in trying to explain all of the mysteries of light and electromagnetism. And we ended up getting to interview and then get to know in person Carver and Mead at some point in the last few years. And it was really, really wonderful to find somebody who had been working on a parallel idea that in many ways overlapped with our own thoughts about it. And then what was really cool was, I know Carver had mentioned Cramer in passing, but I hadn't really looked into Cramer's work. But when I was working on a little piece of a project, we're actually writing a book right now about quantum mechanical interpretations and what the future of that looks like. And I was researching something for that, and I came across your paper, which I have here, actually. It's called The Transactional Interpretation and Its Evolution into the 21st Century. Super cool paper, but I realized that Cramer was actually the initiator of this idea, at least in the temporal sense. He was the first one to come up with this idea that these atoms are coming into resonance with one another. And they use the Wheeler-Feynman diagram to do this time reversal handshake thing, which is interesting to me, not necessarily from the time sense, but from the spatial sense. And so we've talked about that to no end with Carver. And anyways, so we found out about John Cramer, and we interviewed John Cramer, and it was really wonderful to sit down with the man and talk about this idea. And he was really excited for us to talk to you because you have a very different approach, which is, for lack of a better word, I'd say a relativistic interpretation that is transactional in nature. And so you are kind of the third king of the castle here, as far as I can tell, in terms of people who are looking at this very niche topic that we're absolutely stoked on, because I think it gets us closer to understanding what's going on with light and electromagnetism and the connectivity of the universe. Because when we were in college taking quantum mechanics, and the way that light was taught, like these little bowling balls of these photons being shot off into space, it didn't really sit well with us. And so this resonant exchange idea seems to get closer to the heart of what's actually happening, and we're really excited to talk about it. So, yeah, I mean, maybe a good place to start would be what dragged you into this mix. Why of all the topics in physics, you're a philosopher of physics, from what I can understand. What brought you into this one? Why was this the topic that you chose to put this much time into?
Well, thank you for that, that interesting background. And it's always fun to hear, about how people arrive at these questions and this exploration and, this transactional formulation, if you will. For my own kind of history was, I started off in physics because I was fascinated with electromagnetism. That was kind of what first got me into physics. I just was really, my background is my parents are both scientists. My father, who's now deceased, was a solar physicist. And my mother, who's still living, was a math educator with an active interest in physics. So they kind of really showed us as kids. I had a older sister and a younger brother, and they very much kind of brought into our lives the interesting features of physics, including things like, a prism and seeing how the colors of light come out of a prism, that you put in white light and you get these colors out. And so that just I was always fascinated with that. I thought, light is just something that really grabbed me. So, just given the background of, the scientific background, I just ended up majoring in physics. And around the time that I was doing my master's at the University of Maryland, that's when I encountered quantum theory and with the interesting entangled states, that people kind of call I'm trying to think what the idea of having like two electrons that are in a particular kind of state, such that they are. It's called an entangled state, and it's a sense in which these objects are not really separable in the way we usually think they are, and they have a combined state that's kind of somehow like a whole that's just greater than the sum of its parts. And so these I call them quanta or systems. I don't like to call them particles because I think that gets to that more like the idea of this little hard ball that's running around, which is probably not not the way things really are according to quantum theory. So I just found out about these situations in quantum theory where you have these entangled particles and you can send them off to opposite ends of the galaxy or whatever, and have somebody measure the spin, say, it's like how it's, what direction it's spinning in, so to speak, measure it in one direction, and then the someone else on the other side of the galaxy, if they measure that same direction, then their particle must end up the opposite way. It's called spinning up or spinning down. And these kind of instantaneous connections among apparently separated particles, that's what we call non-locality. That really grabbed me, and I said, so this is really fascinating, and I wanted to learn more about that and kind of study that aspect of quantum theory. And then I found out at that time that it was the philosophy department at the University of Maryland that actually had a group called the Committee on the History and Philosophy of Science that was headed at that time by Jeffrey Boob. And they were looking at these very questions. So it was at that point where I finished up my master's and I switched to the philosophy department to work with those folks. And your question was basically like, well, how did I get into this transactional, formulation? It was during that exploration, I kind of started out being, having an affinity or being interested in the Bohmian approach. David Bohm was really a wonderful, profoundly, original thinker in quantum theory, and he wanted to really understand what quantum theory was saying about reality. And he proposed what's called a hidden variable theory that was at least willing to talk about, what's nature really doing, which was kind of, a little bit like you don't ask those questions, in sort of a lot of mainstream physics, they just kind of say, Feynman famously said, don't ask those questions or you will go down into a hole that no one has ever escaped from, because it's just, it's perplexing. And they're sissies. No, I'm just kidding. So, but so
agreed.
You can cut that. But anyway, so I was doing my graduate studies and looking for a dissertation topic and kind of enjoying the Bohmian approach. But then I just happened to come across, I think I was in a library reading a paper. It may have referred to Cramer's original paper or something. And I was like, oh, what's this about? So I just went and got, back in those days, you had to go and check out a library book. It was, and here it was, Cramer's 1986 paper, where he, it was in Reviews of Modern Physics, and he kind of laid out the contrast between what he was proposing and the Copenhagen interpretation. Yeah, so that was kind of a tradition that came up with Bohr, and he was in Copenhagen. So this kind of approach that's, as I said, is really kind of an umbrella term for a lot of sort of attempts to make sense of quantum theory by talking more about observers and what people are, experiencing and how they apply the theory. And it becomes kind of, it becomes, in my view, a kind of an evasion of the basic mission of finding out, what is nature doing?
Yeah.
That in a way that doesn't need to refer to some particular observer and that kind of thing.
I think we can get kind of blinded by our predictive powers sometimes, right? It's like these are incredibly instrumental mathematical formula, right? That arguably give us a lot of potential technologically, but it's very easy to get obsessed with that and sort of pat ourselves on the back without really going back to the fundamental, like, what is our job as scientists is really to explain the mechanics of nature, what's happening, who's causing what to happen and how. And so I feel like that conversation got kind of streamlined. And one of the things we spend a lot of time... Sidelined, sorry. We spent a lot of time trying to figure out when that happened. It's interesting that you point to the Copenhagen interpretation. The Solvay conference is another pinch point. The death of the ether with Michelson-Morley. There seems like something about 100 years ago really formalized this idea that no, like we can just describe this mathematically and move on. And that's really unique in the sciences. You don't see that in a lot of other disciplines where the ability to just articulate it mathematically is sufficient. It's like you have to accompany it with some interpretation of what this means for reality at the end of the day in almost every other science.
Right. Yeah, and that's such a good point, because my opinion is sort of it became a kind of a cultural response among the mainstream scientific thought leaders at that time, around the time when the sort of the strangeness of quantum theory began to kind of rear its ugly head. I don't think it's ugly, but its challenging head as far as what is going on here. And I think if you want to sort of get into a diagnostic mode, my sort of diagnosis would be that we come into our scientific exploration with certain bedrock expectations about what counts as a good explanation, what's a satisfying explanation, what features should an explanation have. And quantum theory, as it stood as a formalism, seemed to foil a lot of the those bedrock principles. Even the way it was arrived at, I talk about this in chapter 2 of my Cambridge book, it's also in the second edition. It came out in 2022. And in chapter 2, where I go over this history of Heisenberg being subject to these kind of classical prejudices. We don't know they're prejudices, but they are kind of baseline assumptions that we all work with that we think a theory must conform to in order to be a theory, and now not some crazy thing, right? So, and among these, they're actually articulated by famous scientists whose names are escaping me at the moment. Huygens was one of them, and I write about this in one of my papers, where Huygens is among the prominent physicists of the past who said, quote, "It seems to me that the test of do we or do we not understand a particular topic in physics is, can we make a mechanical model of it?" Okay, so that was Huygens. Got to be subject to a mechanical model, okay? And then it was William Thomson who said, in the true philosophy, we can see the causes of all natural effects in terms of mechanical motions. And in my opinion, we must admit this or else give up all hope of ever understanding anything in physics. So it's very clear, these are very clear statements of this, out of the starting gate for most physicists historically and continuing to this day has been this presupposition that you have to have mechanical models of things. And so going back to
what do you mean that continues to this day, by the way? Because I feel like it's very much the opposite.
Well, it sort of depends, who you ask perhaps, but my sense from some of the problems that we continue to have in physics and the approaches to trying to interpret quantum theory are that there's still an expectation that there's got to be some kind of mechanism for everything, and that and of course then we can get into semantics. Well, what is a mechanism? But the idea that you have to be able to determine it in a determinate way, be able to follow it from its initial state through to some final state, and be able to say, in terms of local interactions, how it got from its initial state to its final state, and in a way that's completely local. So that's kind of what I take to be the mechanistic. And I mean, what I guess the way I represent this in my talks is, and this is in the sense jumping ahead perhaps in what we want to cover, but we can always go back to it, is that an example of this sort of assumption that a mechanistic account must be given for a proper theory is in fact quantum field theory itself, because the way quantum field theory works, and quantum field theory is, it's a very sophisticated theory that is often used to describe high energy interactions that go on among systems and so on. And it works very well to give us probabilities for what we're going to see. But its underlying picture is very much what I call a bucket brigade. So the way quantum field theory works is that you have something called a field operator, and this is a theoretical entity that you assume is associated with every space-time point, and that it is these field operators that act as little kind of bucket brigade firemen, if you will, that carefully hand the little localized nuggets of energy from one point to the next point. And that is a mechanical picture. It's like you've got to be able to say what's going where, and it has to be very local, and it has to take time in a metrical sense and so on.
Yeah. Are those operators objects or bodies in the traditional classical sense, or are they more mathematical structures?
They are mathematical theoretical constructs. And see, that's what's such a great question, because then you get into the question of like, well, what are these operators? Are they literally in space-time? You say they are associated with space-time. What does that mean? So this is where it's a construct whose physical referent, if you want one, or physical correspondent, is left unstated. No one knows what it is. You don't really talk about it. You just say a quantum field operator is associated with every space-time point.
So
and that's the crazy thing, because it gives this illusion of mechanism.
Well, I think the word mechanism is okay, but mechanical seems to fail completely at that level.
Well, but even mechanism, right? Like if you really cleave to a historical and traditional understanding of what it means to have mechanism, it's that you have bodies that are interacting that produce the observed effects. And so if you come down to it and you say, okay, well, there's an operator and we have some mathematical description of said operator, but let's not get into the weeds of what gives rise to that mathematical description, then I feel like you've created a shell of understanding that works because you're able to do math with it, but you never get to this deeper question of, okay, well, what's at the foundation of nature?
I don't think it was an accident that the venerable ones used the word mechanics as opposed to mechanism. I think they were really trying to point at something like a machine with parts that do things.
Yeah, and again, this kind of gets into, what do we really mean by a machine? What do we mean by, making a mechanical model of something? And that could be an interesting topic in itself. This is what philosophers of science will, be happy to chop down a bunch of forests and, write papers on that forever. So, but I guess for me, it's this insistence that everything that happened at a fundamental level of nature must look like stuff that happens in our ordinary experience. We must be able to see it. And it's basically asking for violations of the uncertainty principle, because that's what things look like. We think when we see a pitcher pitch a ball, we think we see how fast it's going, and we think we see where it is. And that to me is kind of the kind of explanation they want. They want it to look like ordinary macroscopic experience. Okay, I'm turning a crank. I can see everything that's happening at every stage. Nothing's going to surprise me. Nothing's going to go faster than the speed of light. It's all going to be like my little machine. So that's the sense in which I use the word mechanical. That it's comfortable because it doesn't challenge the kinds of phenomena that I'm used to experiencing. And so, that's what. And in fact, the crazy thing was with Heisenberg is, back at the time when the classical, nice, mechanistic, locally well-defined at all times, classical physics was breaking down, was not able to account for things like atomic spectral lines and the black body spectrum, energy spectrum, and so on. And so they were searching for another theory, and they were kind of just grabbing it at ad hoc stuff that seemed to work. But before that, actually, before they succeeded in at least getting it something ad hoc that worked, Heisenberg was trying to make mechanical models. And he talks about this. And in fact, I forget where I read this. It's some interesting, I wish I could try to follow up and figure out where did I read this. It may have been in a book called The World of the Atom, which was a very nice compendium of historical writings by the quantum pioneers. He was struggling to build his little Rube Goldberg mechanical model. And he says, everything failed. Nothing failed. It was obvious this was not going to work. So I tried a different approach completely. And what he describes, it seems like to me, like, this is me interpreting, that like he had a Zen moment. And he decided to just do a Zen beginner's mind and say, let me stop trying to impose my preferences on what I think nature should be doing. Let me instead go into a more receptive mode of looking at what's the data? What do I know? What can I really say is true, or at least is concrete? And, it's this, these have got these energies and these energies. And he started looking at the relationships of the energies and the transitions between energies in atoms, which is just basically an atom having an electron that's jumping up and down in different orbitals, so to speak, and jumping to different orientations with respect to the nucleus. So, yeah, did you have a question?
It seems like you're pointing to the idea of mechanism being this internally consistent story that is told, that accounts for all of the observations, everything which is known, which is logically consistent, and goes from one place to the next. Is that a reasonable restatement of your conception of mechanism?
Actually, the way I'm using it is not really in terms of ideas or concepts, but it's in terms of phenomena. So it's in terms of it's not so much, an account where you can say, at every stage of a process, well, what's going on with this process? That to me is a more general level that I would not want to get rid of. I wouldn't want to just kind of hand wave and say, then a miracle occurs, or something like that. But what I'm really talking about is the specific kind of proposed account that wants to have things in space, time, in space, and in time that you could conceptualize. If I could shrink myself down enough, I'd see a very tiny little machine that I would be able to look at and see in a sequence of well-defined time exactly what's going on. So it's really more phenomena based, and it's really that bucket brigade picture of the idea where and a counterexample. For instance, here's one physical notion that violates the kind of mechanical idea I'm talking about that Huygens had and Thomson had. Is the so-called absorber or direct action theory of the Wheeler-Feynman and other people and also Cramer. And the reason that theory violates this mechanistic or mechanical kind of demand is that it seems to require an instantaneous non-local connection among the sources of the field. And that's not where you can go, oh, look, I see where the energy, no, it's instantaneous. And that's why it's called an action at a distance theory. And that is what is taboo. And that is one reason why the transactional formulation has been kind of not welcomed, because it violates this idea articulated by Huygens and Thomson, and that's why I say, going back to very much today, there are still maybe they wouldn't state it as explicitly as these folks did back then, but there's still a kind of a sense that action at a distance is some not wrong thinking, not legit. It's not scientific. So that's really the core. It's what kind of stuff is happening, and in the action, so-called direct action theory, stuff is happening that is not amenable to that kind of what I'm calling mechanical model. So
I'm not sure that it is. I'm not sure that it's necessarily unamenable to it. When I was talking to John, and actually, like, for many years talking to Carver, the reverse time idea in the context of space-time, space and time are to some extent interchangeable. And so you can imagine these atoms being linked structurally to one another. And I think the defensible position with that is the probability distribution function for the electron, which is essentially the outer surface of the atom. We get these pretty orbital diagrams in chemistry, but they actually ignore the tail distribution of the electron distribution function, which actually goes indefinitely. And it actually gives a sensible means for atoms to be connected to their neighbors physically through structure, through the actual surface of the atom to one another. And so when I asked John, like, whether that could be a physical connection between the atoms, which would be sufficient for the atoms to both participate in the transaction, he kind of said, he thought for a second, was like, yeah, but I don't know that it gives you anything else. And I think this is what it gives you, is it gives you the ability to obey the Huygens-Thomson principle and still stay in the realm of physics with it. So I don't think all hope is lost with that.
Yeah, I guess it all kind of comes down to, what do these guys really have in mind when they said a mechanical model? It's certainly, and but the other kind of lurking questions that come up in that kind of issue that you've raised is the idea of the nature of space, time, and the nature of the physical nature of things like wave functions, and so the tricky part here is that, so if we want to be realist about them, which I am, I'm not. Now we have to get into a little technicality that may seem like nitpicking, but it's probably important, that the notion of a wave function is actually a non-relativistic approximation that does break down at the fully relativistic level. So, and that is because the term wave function simply means, and here we're getting into more jargon. So,
that's cool. We're good so far.
We can just kind of skip it if we want to, but a wave function is just a fancy name for another fancy term called probability amplitude. It is simply a probability amplitude that that a particular position eigenvalue will be found. But that doesn't work at the relativistic level, because position is not an operator at the relativistic level, so you don't really have any position eigenstates for real. So the weird thing is, this is where
can I just rephrase that? It sounds like you're saying that a wave function talks about something probabilistically occurring, but it doesn't necessarily talk about who's doing that action in the first place. Therefore, it's not really it's not really a spatial actor in that sense.
Well, yes, but that is absolutely true. the sort of the deeper issue here is that we can, for instance, for that kind of entangled state that I was talking about earlier, where we have two or many, say, different quanta that are entangled, is that they have a collective wave function. And that wave function, I mean, at least as a non-relativistic approximation, that wave function is 3n dimensional and complex. So the mathematical character of this wave function is not something that fits into the space-time manifold, 3 spatial, 1 temporal parameter. So
it's like a relational map in some sense, right? I think that's what we're trying to separate out from the physical everyday reality. It's like it's got nested abstractions involved immediately. And so you're not just talking about like the shape of a computer or something like that.
Yeah, and I'm actually, realist about wave functions, or at least about these probability amplitudes, that you can define them at all levels for, say, momentum. You can say there's a momentum wave function that you can define, in a strictly correct way for all levels, including the relativistic level, because momentum is more fundamental. But I take these entities as having some form of reality, and I illustrate this in terms of the iceberg kind of metaphor, where there's an iceberg, and we know that a whole bunch of it, like, I don't know, 7/8, I don't know, there's some correct fraction, if I knew it, that is submerged, and it's the bulk of it. So what I think of is that the space-time sort of phenomenal concrete level that we think of as reality is not the whole reality, and that is what is underneath, that is sort of hidden from us, is really these entities that are described by these crazy complex, many-dimensional Hilbert space. That's the mathematical form for these states.
I think in terms of everybody's everyday lives, that's completely reasonable, right? Like my experience on a daily basis is so much about my relationships to people, and so much about this internal spiritual landscape that I have. That's, there's an argument to be made that the world is principally made out of the stories that we live out, just as much as it's made out of the atoms that compose our bodies, right? And so I think there's really some merit to that approach, despite the fact that we're departing from perhaps the basic three-dimensional reality that we're used to, because that's just not what makes our days up for the most part.
Well, that's so important. Yeah, I mean, I love what you said, because I do think, when I talk to sort of people on the street, lay people, and they're like, many of them say the kind of thing you said, where, yeah, of course, my experience is so much richer than, oh, there's a car going from here to there. Oh, it's just so mundane, right? And that's, I mean, again, then the question is, what counts as physics? And I mean, the tradition in physics has been to kind of act like, oh, well, that stuff, what's going on in people's heads isn't my concern. I'm going to talk about what's real, and what's real is not what's, and it's kind of antisocial in a way.
But they're trying to get into the atoms' heads at the same time, right? It's very similar.
They would probably deny that. They would. I mean, it's very much, if you want to do the Plato thing, right? Where, Plato's cave is our just external mundane, okay, it's what's just kind of hits you over the heads in terms of your five senses, in your external five senses. And then the other stuff is obviously internal, more subtle, more relational, more, it's not like a third party corroborated evidence kind of stuff. And I think what physicists want to do is just say, well, look, it's not our job to address those other things. Our only job is to, in terms of the Plato's cave metaphor, look at these shadows on the wall. Because, the Plato's cave allegory is that there's this whole rich world, but there are prisoners who are chained, so they can only look at a wall and see shadows on it. And so physics is almost like, look, I'm dealing with the shadows, guys. and just shut up about that stuff out there. Get away from me. You're not doing physics. And and the sad part is what they've come up with, what they've been forced to come up with in their shadow play is actually pointing to something that's out there in the world, but they're so determined that doesn't fit into their metaphysical and epistemological, operating parameters, that they want to say, no, that's not, either that's nonsense, and you're stupid for thinking about it, or if they're a little more humble, that's just beyond my pay grade, or that's not my job as a physicist. So there's this.
Can you see how the Hilbert spaces, though, and the n-dimensional realities could be, in some sense, an attempt to reconstruct what's beyond the cave?
Well, they're, metaphorically speaking, they're kind of pointing to it, saying, look, guys, if you want to understand the behavior of these shadows, there's stuff out there that's giving rise to them. Hey, if you would just look around, there's a guy with a giant jar in his head wearing an interesting colored robe. If you just turn around and look, he's in Hilbert space.
Yeah.
But what I get is things like, you don't want to reify Hilbert space. That's stupid. That's just that's a mathematical construct. And it is true in a sense. That's how Heisenberg stumbled on it by accident, because he took the data and put it into what he called laundry lists, and they're actually matrices. He didn't know what matrices were, but he said, if I make an array of this and I interact these arrays and I do this mathematical operation on them, lo and behold, look, I get the right transition probabilities and things. I can start to predict what I'm seeing. So he just stumbled on it because he stopped trying to create kind of a Rube Goldberg, tinker toy local sort of model, and he came up with a formalism, and that formalism was actually coming out of Hilbert space, if you will, or the so-called domain that transcends the cave. And that's one way to interpret it. I mean, a lot of people will say, okay, well, quantum mechanics is a formalism for predicting my experiences. And I'm like, well, okay, good for you. It's like they don't, because it doesn't obey their rules for what counts as physically real.
I mean, the danger of reification is not primary in and of itself. So, look, we love poetry, we love art, music. These are all extremely abstracted maps of reality. And so I think the only danger is when you start mistaking the map for the territory itself and start studying the little wrinkles on the map as if they're actually part of the reality that you should be obsessed with. And I think that's why people are so allergic to it. But that's a far cry from saying that a map isn't a useful way of approaching navigation at the same time. And so I think we have to be really careful with that term, because it's not an outright terrible thing to reify to create abstract actors in order to convey a point. I think it can be quite useful. Engineering would certainly prove that out, that these mathematical models have been quite useful in terms of all of the electric technology that we use today. Nastia looks like she's got something on the tip of her tongue.
Well, okay. So I've been stuck on this idea of, if you throw a baseball, it gives a very simple perception that you can see how fast it's moving and you can see where it is. And I'm like, okay, so if you have the way that you would really be able to tell velocity and momentum is you'd have to take a series of photographs, and then you'd be able to say that here is the ball, and based off of how far it's traveled between these two snapshots, we can tell how fast it's moving. And if we have some other information that we can gather from it at the very beginning, then we can...
A guy getting hit by the ball at the end.
Yeah, and depending on the size of the bruise, you can probably figure out momentum.
Yeah, walk the better.
And so I'm like, when I start to think about the quantum realm and the mysteriousness of the uncertainty principle, it immediately occurs to me that perhaps it's a measurement issue, where if you had a device that was able to interact with the body, the particle, the photon, the electron, whatever you want to call it, in such a way where it could take a picture of it as it moved, the atom or whatever, you'd be able to get all of this information from it. And it's the fact that our detectors are inherently structured in such a way that we disturb the object through the act of measurement that we come out the other side and we're like, well, we can only have momentum or position. We can't have both. And I'm like, but in a theoretically ideal world where you had an ideal detector, the same way that a camera doesn't affect the motion of the ball, wouldn't you be able to circumvent that theoretical impasse?
No, it's actually the theory itself that forbids your ability to describe, at least to describe, say, an electron by a momentum, a well-defined momentum eigenstate, and also a well-defined position eigenstate. It's the formalism of the theory that says, I'm sorry, you can't do that.
Sure, but
it just so that, in other words, that then you can only measure one or the other. When you measure, you have to pick what observable you're measuring. So if I want to measure position, then you have to basically beam a very high energy photon at it in order to localize it, and then you have localized it, so perhaps you've made it, crash into a detector or something, but then in doing so you have made its momentum completely uncertain. So there's no way that even in a formal sense you cannot apply a precise momentum and a precise position to any quantum system.
But that still sounds like it's a problem with the methods that we use to be able to probe these systems. Because you're like, in order to be able to measure it, you're beaming something at it at an energy level that is commensurate with the energy level of the thing that you're measuring. And so
you'd like a measurement independent statement then, really.
Kind of. Well, it's just, I'm like, to extend the metaphor of photographing the ball that's thrown. The photograph doesn't disturb the trajectory of the ball. It doesn't affect the movement of the ball at all. And that's why you can use that to be able to determine both momentum and position.
Oh, I see. So that now we get into kind of the scale of things. So with a baseball, sort of with what we call macroscopic objects, they are they do have a spread. They still have a spread, but due to the fact that they are comprised of enormous numbers of systems, and in fact also the fact that they are intra-acting in a sense, they're kind of constantly self-measuring and relocalizing themselves. And then the amount, and because if you look at the math, what you will find, and this may be something I can follow up and send you as a little applet or something that will demonstrate that as an object, it's more complex and has more degrees of freedom that comprise it. It seems to be more localized, and it seems to be more immune to the uncertainty principle. The clunkier it gets.
And that makes sense. That makes sense because when it's clunkier and it's got more things that it's interacting with, it's stabilized by those interactions. But I'm like, if the camera that you were trying to take a picture of the ball with worked on the following principle, which is that the camera actually threw rocks at the baseball of known mass, and then your detector was behind the path of the baseball, and you would be able to see the deflection of your rock throwing camera in relation to where that baseball went. That's kind of the equivalent of the tools that we use to be able to measure the subatomic world, is that we throw something at them, we see how they deflect, and then we're like, well, we cannot measure both momentum and position. And it's like, well, yeah, it's because you're throwing something at it and you're destroying the system. Like, the ball never gets to where it's supposed to be going.
Well, sure. I hear what you're saying. The key thing here is we have to distinguish between issues involving measurement and issues involving description of the system itself independent of any measurement. So it's at a more fundamental level. If we don't want to say get bogged down in issues of, well, I'm disturbing something just because I'm throwing rocks at it, which of course is a no-brainer, which is true. But the problem with the electron is that independent of any measurement, if you say you prepared it in some state, so you do have to know anything about it, you've got to prepare it in some state. To have any, or you don't have to if you don't want, but if you want to be able to analyze what's going on with this electron, then we have to sort of start somewhere. So, well, I mean, we could take, if we didn't want to intrude too much and didn't want to get into issues of measurement too much, we could say, okay, I got a hydrogen atom and it's in its ground state. So that means there's one little electron down there in a well-defined energy state. That's what it means to be a stable hydrogen atom. I got a happy little electron in its ground state. It has a well-defined energy. End of story. So that means I could describe it by what's called an energy eigenstate, has a well-defined value of energy. That means that the time that it is anywhere around in its orbit is indeterminate. I mean, literally, there is no fact of the matter about when that electron is at some particular place in its orbit. It's everywhere at once. It's non-localized. It's just, and that's the nature of being in an energy eigenstate. So this is where it's the theory itself that just sort of tells you, I'm sorry, if you want to be able to say that my energy is well defined, then that means I have no the what's called the complementary observable to energy is time. And it's very similar to if something has had a well-defined momentum. You could say in atoms it's a bit more complicated. They can say have a well-defined value of angular momentum. And then the theory itself says there is no fact of the matter about physically where that electron is around its orbit. That's what the theory says.
I mean, it makes perfect sense if you define energy as something in motion or the potential for something to be in motion, then it makes sense that you can't determine the energy if it's not in motion. Like if you stop the system to evaluate position, then you don't have any energy in the system anymore. But
I get Anastasia's concern about, I think this should be understandable independently of, how we're measuring it. And I get that. And they do go together because it's sort of like nature in obeying this theory it's a result of the fact that, a nature obeys this theory, that it's going to prevent you from trying to measure these two things at the same time. It's not going to let you, but it's because of the theory. It's because these things, and at a very fundamental level, what I've argued is that space and time do not exist below the iceberg, so to speak. So, and in fact, this gets into maybe broader flights of fancy. You may want to go back to something else, but the atom itself, if you've got a stable atom and you've got an electron in this momentum eigenstate, then literally that's why I call it a cloud. That's why they call it an electron cloud, because literally there is no fact of the matter about where that electron is. So this, in a sense, is what gives matter its stability. It makes it, if that atom, that electron has a well-defined energy state, then you can try to push on it, but you're not going to be able to compress it, beyond a certain point, unless you really start bombarding it again with the equivalent of rocks, and then you disturb it. Then it's no longer in the energy eigenstate anymore. If you disturb that energy eigenstate, okay, all bets are off. But it's stable, so that's why you can't squash an atom unless you really go to extreme measures. And in fact, it's historically true that if you had, and factually true, the classical theory that described electromagnetism would never have stable matter, because it would have electrons radiating as they accelerated. They radiate away all their energy, and you wouldn't have atoms. So we can thank quantum theory for giving us stable atoms, even though it comes with some other weird stuff.
But it's like, if we accept that the electron is not a little bowling ball that's in orbit, but is instead this area of influence,
activity,
then it makes perfect sense that you can't localize its momentum, because I'm like, well, what is the thing that you're trying to localize in the first place? It's an area of activity that has some energy associated with it. And the entire question of being able to localize it to say that this is the momentum of this thing is silly, because we've all agreed that it's not a bowling ball that's in orbit around the atom. And so it seems like a confusion that is unnecessarily like spookyified, because I'm like, well, it's not a body the way that we think about it. It's kind of this like goo that just surrounds the atom that's doing something. And so you can say that this goo has some amount of momentum, but to say that this goo is in one place beyond saying, well, it's around the atom, seems like it's not even.
It's a flowing goo, though. It's not just a static goo, even, right? So it has motion inherent in it, intrinsic angular momentum, and so forth.
And so I'm like, is that really that surprising, or is it?
Well, I think what makes it seem surprising is that we do get what we call particle-like, well-localized phenomena from these things, and that's the wave-particle duality. That's right. So that's where that sort of consternation comes in, and in the transactional picture, that whole paradox is resolved, because again, the only time you get particle-like, well-localized phenomena is when you're doing, what's called a measurement. Measurements are happening all the time, whether or not there's somebody with glasses, deciding to do something. It's a kind of interaction. It's basically a photon level interaction, and there's a lot of energy around. So stuff is always getting localized, and so that's when you get basically when you measure. If you go, okay, like Anastasia said, this electron is just goo. Okay, fine, but I know that under certain circumstances, I can get a whole electron charge to show up in a very small place. Wow, that's so cool. I want to do that. Okay, well, to do that, I have to basically, again, this is what you got to do: fire a high energetic photon at it, give it enough energy to get out of the atom that it was in, and then you've basically given it a whole bunch of energy and momentum due to its interaction with the photon, and now it's going to just go somewhere else and get absorbed by some other atom, and it's going to give off energy. It's going to lose energy when it gets involved in that other atom, but atoms are small. So you see a phenomena happening that, oh, look, I see a spot of different color on my photographic film. That's because this electron got absorbed by an atom. And so, so it's basically interactions with photons where they're not little bowling balls either, but transactional kinds of interactions with the electromagnetic field that lead to these localized kind of phenomena. So it's not like the thing ever really stopped being a blob of goo, but its properties became such that it led to a localized phenomenon.
I think that it all gets a lot easier to comprehend if you think about the electron as being a state of the blob of goo. So if the atom is this blob of goo, the electron is a particular state of that, and it has different energy levels, right? Different vibratory modes to it. And when you start thinking about atoms as these blobs of glue that are somehow connected to each other, exchanging that energy, right? Really just resonating with one another in different fashions, that's when the transactional interpretation comes to the rescue, as far as I can tell.
Well, yeah, and I mean, I think that you're right that there are lots of ways to kind of get comfortable with, the seemingly ill-defined nature of these little objects, because we are so used to thinking of them as particles, and they aren't really. That's an abstraction. That's something that Ian McGilchrist talks about, the left brain and right brain kinds of thinking. And that's kind of the left brain saying, my everyday mundane experience, I see things that look localized, and I see things that are like little objects going from here to there. So that's what everything has to be all the way down. And it wants to abstract. So that's what we tend to do.
Yeah, we got to put handles on things, right? It's you got to have a way to grip stuff.
Right. And it's very much harder to grip these subtler entities. And the whole thing about the transactional picture, really, where it provides the most aid is in, ironically, we don't want to be instrumentalists, but is in being able to help quantum theory say what counts as a measurement. Yeah, that's the measurement problem.
Okay,
So
say
that's
more about
really
that. Say more about that.
So yeah, so the measurement problem of quantum theory is really an affliction of the conventional way of formulating the theory that again makes use of that kind of bucket brigade picture of the way fields propagate. This kind of demand that a field starts somewhere and then progress through something, I don't know what, in a process you can track, at least conceptually, and end up at the end at someplace else. And it's kind of a very autonomous process that's considered local in a sense, or quantifiable as coming from one thing and going to another thing. And what happens with that is that the theory can never say, when I start with something and then other things combine with it and they start interacting, at what point does something become a measurement? Where do I get an outcome? It actually cannot tell you why you ever got an outcome. It can't tell you what are you doing that constitutes the condition to get an outcome. This is why you get Schrodinger's cat. That was actually, Schrodinger was what he was doing. He was saying the theory has a problem. Well, what he said was, I don't like it, and I'm sorry I ever had anything to do with it. That's a quote. And it's because of this deficiency in the theory. Now, what TI does is it says, okay, your fields don't actually work like that, and they do have a fundamentally relational character quality where sources of the field, like electrons, and we're talking the electromagnetic field, are actually in constant communication in a sense. This goes back to what you said, that what the charge means is, in a sense, that they are always connected by this basic time symmetric field. And what that means is there's no fact of the matter. It's not like a field is coming from this one and going to that one, or there's no definition about where the field originated and to whom it's going. It's a two-way, it's a mutuality. And that is the basic interaction for the direct action theory that underlies the transactional formulation. And under certain limited circumstances, they're very strict circumstances, that energy conservation has to be satisfiable, and that's the main thing. And that there have to be states, like they have to be bound, so like in an atom, so that they can absorb energy or emit energy and have a stable state to land in. So these conditions have to apply, and if they do, and again, this is a probabilistic process. It's indeterministic, but there's a probability that, say, if this atom was in an excited state and this one was in the lower ground state, this atom at some point will engage in a transaction, and that's when you get a directed field from this excited atom to the unexcited atom, and you get a photon. The photon is a mutual creation. It's created literally by both entities. And often there are many more than, one absorber. So this is where you have different probabilities that the photon will go to different absorbers. And that's what.
And I think just by enjoying the conception of bringing two players into the story that are important, it has this. It satisfies our intuitive need for this. Well, we understand thermodynamic equilibrium really well, for example, right? We understand that if you put some hot stuff next to some cold stuff, that there's going to be this leveling out over time. That's a very easy to comprehend and natural process that everybody's familiar with since they're 5 years old. And I think that this brings that intuition back into the picture in a really beautiful way.
Well, yeah, it is very natural. I mean, like if you want to sell your house, okay, I put my house on the market. If no one's interested, I'm sorry, you didn't sell your house.
Right.
Right? And that it's not a one-way thing. You can't just be like, please take my house. You've got to have at least two parties involved for anything to happen.
Yeah.
And that's the problem with the conventional theory is it has this, death grip. It has a death grip on that unilateral propagating field that nothing ever happens.
Yeah, it's so interesting.
And
It's
I mean,
interesting.
yeah,
Go
go
ahead.
ahead. Well, I call it the yang only picture
Mm.
because I just kind of recently became more aware of I've always known about Taoism, but I started thinking about that, and I just realized that that the absorber, the response of the absorber, the mandatory necessity for the absorber and its response is a yin thing. That's a yin process. It's like someone there to hear you and to respond to what you say, and that without that, and again with the house sale, you've got to have a buyer, you've got to have someone who's yin, who wants to receive, who wants to negotiate, who wants to have a mutual communication, and then something happens.
I often think about this as an artist, as a musician. It's like it is satisfying to some extent to play music by yourself in a closed room, but it's orders of magnitude more meaningful to do it in a room of people who are also enjoying this, and you're all kind of creating something, and you can get into this. There's something about the audience's participation in it that really does make it a profound experience that I don't think you can have by yourself. And so
Absolutely,
it seems
it's about communication.
it's like why we have
And
friends, right?
I was involved in sacred choral music, in sacred a cappella music too. And yeah, so it's completely different, just practicing in a room by yourself or being there. It's a collaborative thing and something happens, definitely.
So why is this interpretation not more popular?
Well, there's a whole, diagnostic manual I could give you on that. Part of it is again, those very deep-seated prejudices and desire for the yang only picture, if you will. The field starts somewhere and then it goes somewhere. You're stupid if you don't get that. And it's like it just seems obvious that that's how things have to work, and it's very hard for people who have kind of been marinated in that their whole lives to let go of it. And then there are, people say they don't like the backward in time aspect because, again, a macroscopic experience does not support that. But again, then the subtle point is that really at its relativistic level and being fully realist about, the entities that are involved in the transactional picture, these entities are, again, they're not really space-time objects. I mean, you can't consistently say that offer waves and confirmations and so on are going around zigzagging around in space-time, because it's an incoherent picture. Another thing that's incoherent about it is that if you literally have stuff going forward in time and then backward in time, then stuff's coming from the future, and that means your future is already set, and you're helping yourself you're stipulating all measurement outcomes in the future, and you've got a block world. So you've sort of smuggled in, without realizing it, a block world ontology, which means you've already helped yourself to all events that ever happened, that ever will happen, and they're all there. They're already there. So the narrative about, well, there's this going that way and that going that way, and I'm like, no, nothing's happening. You've got all your events. You do not need any more stuff going. There's nothing. It's just talk. It's idle talk that's overlaid on top of, you stipulated all the events that were ever going to happen. So you don't need to account for any events because you just helped yourself to them.
Isn't it strange that we're so uncomfortable with atoms planning for the future, but in our own lives, any living system is completely based on the future in some sense? Like I feel like I'm constantly being instructed by the future because I see a future that I want to see happen, and I act in accordance to make that future come out the way that it does. And I'm not trying to insist that the atoms are conscious or anything like that, but it does seem to be a very comfortable aspect of our daily existence that we, for some reason, feel very deeply uncomfortable with happening at the fundamental physical reality.
I'm like, okay.
Well, yeah, here's where we need to kind of figure out what we mean by the future. So we have something to clarify, maybe. Did you have something? Did you?
Well, no, the way that we talk about the future influencing the present to me seems like and the discomfort with the future influencing the present seems to be a lack of realization about the way that permissivity works in the world. Like if you're standing somewhere in time and you're looking at your life and you're like, okay, this is what I've done with my career up until this point. I have been an expert in, geophysical engineering. And you decide that actually what my greatest passion is I want to be a painter. There is a series of actions that you have to take in order to get to the fate of turning into a painter. And the vision of what that future looks like is the way that you are constantly orienting yourself towards that and moving towards it. And there's going to be things that prevent you from doing that because, say, you've never picked up a paintbrush before, say you have all of these things that prevent you from it. And you, one by one, have to break down those barriers in order to be able to move in that direction. And so I'm like, obviously we're constantly in contact with the future. And so it seems entirely possible that atoms on a far less intelligent level are also in communication with the future.
Aware of their options?
They're aware of their options because if we're talking about energy...
That's the key. That's the key. Options. See, now, and this is where when I want to talk about future, what I mean, like the way I've been kind of criticizing the zigzag picture is there's maybe a technical point here, is that rather than have what I would call an actualized future that it composed of single events that are incontrovertibly there, we can allow for possible futures, if you will. And so all of this possibility, so this is another important aspect that I think we have to kind of come to grips with in the full transactional formulation. And I represent this by the knitting metaphor. Okay, so it's not like, it's not like I want to say the future doesn't exist. The only way I want to constrain this future talk is by saying it's not actualized. It's not a block world where everything it's going to happen is already out there as an actualized event. So really what I'm saying is I dissent from actualism about the future. So this kind of notion of having options is so important because, again, that's where the level of possibility comes in this sort of submerged part of the iceberg, which can be sort of mapped as Hilbert space, or mapped, it's, the territory I think of as possibility. And the map of that possibility is the kind of quantum structure, the formalism, the Hilbert space formalism. But that territory, again, is rich and it can have an internal counterpart so that people are, like you just said, internally aware of, well, there are different options for my life. And which ones am I going to actualize?
And do I have the energy to actualize it, right? Do I have the energy to actualize that possibility?
Yeah, and that's where volition comes in and intention and all these things that are kind of not traditionally part of physics. Maybe they don't need to.
Well, they're the energy state, right? They're the paired energy state. They're the potential between the two energy states of the two, the emitter and absorber. Like that's really like, do I have the proper, heft to get this transaction accomplished or not? And if you don't, somebody else will.
There's an element of intention there. Yeah, exactly. Right. So maybe there is some kind of element of intent where it says, okay, we're going to do this transfer now.
Or it's just, it's just buzzing. It's too full of energy, right? It just needs to dissipate, just like any other energetic structure, right? And there's going to be somebody who's appropriate to that transaction out there to take up that energy.
Right.
And a lot of people, atoms that aren't.
So this is where this really starts to get interesting to me is, okay, so you have an atomic structure that has energy that it wants to dissipate, and the future contains options. Is there some way to predict which option it will choose?
No. So that's the weird thing. That's where we get the probabilities. And, we can have probabilities say there are like 3 absorbers, so 3 atoms out there. They may have different probabilities for being absorbed, and technically you could arrange that by having, them at different distances, measurable distances from the emitting atom. But yes, so they are fundamentally probabilities. So you could say, well, I've got, a probability of 1/2 that that the photon will go to this closer atom, and maybe a probability of 1/4 for both of these other ones that are both equidistant. But you cannot predict which one it's actually going to go to. You're just going to have, if you repeated it over and over again, you would get those probabilities. But that is the sort of fundamental indeterminacy of quantum theory. And that's kind of interesting too. I mean, some people act like, and again, this is where Huygens would say, okay, you didn't explain that because you didn't make a mechanical model of why the photon went to this one and not those other 2. Because he wants it, determinism is part of that mechanical model he wants. So,
and it might be just lack of information.
If determinism were true, we would not have any real options for our lives. So,
well, there's randomness involved in it, right? So if you have a sufficiently detailed model for the randomness that's involved, then it's possible to say, so if you have these 3 different atoms, one is closer, the other one is, and the other ones are farther, and the one that's closer is moving, right? I mean, like, none of these things are stable, and so there's a degree of freedom of motion that it has, and if it's in slightly the wrong position, then the signal will go to the atom that's farther away, but because of the fact that it's closer, its range of motion allows it to accept the signal more times than the ones that are farther away. And that seems to me...
Well, sure, you can definitely give a good explanation of why some are, why that one atom is more likely than the others to get it. But what people like Huygens would not be satisfied with is saying, but you cannot explain for any given trial,
which one it'll be.
You can't predict which one it's going to go to. He would not like that.
It just seems like we don't have enough information at the end of the day. Like, Huygens, you're going to have to be patient until we figure out better ways to understand what exactly the atom is doing in these vibrational states.
Well, it also seems plausible.
The theory itself is not deterministic, though. I mean, the theory itself says there is no deterministic account of which one it goes to. Now, when people wanted to get a deterministic account, that's when they put in hidden variables.
Mm-hmm.
So that was, the Bohmian thing says, okay, well, I can tell you why for each case, the reason that particular atom got it is because the little hidden variable corpuscle went that way instead of some other way. But there are kind of a lot of ad hoc features to that, and they just kind of have to help themselves to the probability rule and not really say like where that came from. And then there are also critiques of that where it says, okay, guys haven't really explained what about this corpuscle is giving rise to a result. So you just have a many worlds interpretation. So this is Harvey Brown and David Wallace have actually written a paper where they say, you haven't really explained, just because you want to say there's a corpuscle there, you haven't explained why that gives you a measurement result.
But so that's so cool. Like, that's really cool because it says to me that there's a better theory coming down the pipes at some points in the future of humanity.
But is it predictable? Like, even with hidden variable theory, like, is it actually going to tell you for each given trial which one it'll land on? Because it seems like the answer is no.
It's a retroactive attempt to explain. You can't predict it. You can't use it to predict. And to me, it's an ad hoc account. Like you can just say, well, there's an initial distribution of these corpuscles, which are added into the theory because I want determinism in it, and they are just ad hoc distributed according to this Born rule probability distribution. But whenever you get a result, it's because that's where the corpuscle was. So it's an attempt to kind of say that everything was really deterministic, but it actually doesn't work when you look at some recent developments like the Wigner's friend thought experiments. There's the Froschiger-Renner paradox, which kind of uses this idea of it not being clear where a measurement outcome happens, and saying that, there's like an inner observer playing the part of the cat in Schrodinger's cat in the box. And this inner observer gets some result. So he thinks collapse has occurred, but the standard conventional theory denies that any collapse ever actually occurred. And then they end up having an inconsistency where the two observers predict different things. And this is a defect of the standard theory, because again, it can't define when measurement occurs, how an outcome occurs. And even the Bohmian theory that has these hidden variables has problems with that. We get into technical stuff here, but that it starts to get into inconsistencies in like what kinds of states it has to use to describe its particle and so on. So, excuse me.
I want to go.
My impression is that the hidden variables approach, where you're trying to get back to determinism, it just doesn't quite work.
I think that we should take a quick break.
Okay.
Okay. What's
no,
your question?
It's fine.
Let's
get back to it.
You want to write it down?
Yeah, no,
Okay. So let's take 10. We'll be back at 45.
Okay, great.
Okay, excellent. See you in a little bit.
Hey guys, quick interruption. Just a reminder, we're entirely listener supported. That means that patreon.com is the place where you can make sure that this podcast continues to improve, continues to grow. Make sure that we have more and more time to devote towards this project. It's the only way, essentially, right? We're not selling things and we want to keep it that way. So consider coming over to patreon.com/demystifysci. Check out what's going on over there. We have a beautiful community of people. Get together once a week and I'd love to see you there. So check it out.
Shyla, what was your burning question?
Yep. Yeah, so you said something really interesting about if we had a deterministic model, deterministic physics, that there'd be no room for free will. And I think that's a really interesting idea because it assumes that physics is the governing force in the universe and not biology. Because, of course, I can determine how to move my atoms any which way and no physical model could ever predict my behavior in that sense, because bring in this Schopenhauer idea of the will, right? And so I'm not sure that physics gets the final say on something like free will. But I'm curious why you say that.
Well, it doesn't. It doesn't. But I think what physics needs to do. I mean, it's not getting the final say. My point is simply that for consistency, like if we want consistency across the different sciences, then and if we do have free will and we do have live options, then independent of what any particular physical theory would say, it seems as though it can't be the case that what I'm going to do next year is in the world as an actualized event.
Mm-hmm.
If that's the case, then it's not up to me. So it's not so much the world of physics and what physics has jurisdiction over. It's about the ontology that we're going to deal with. So if we're going to assert that that events are all kind of spoken for in a sense of conforming or respecting formal laws, however they're formalized, that seem to say that for a given starting point, there's a given input there's a single unique output, and that if everything obeys these laws, then that output is going to happen no matter what I do. So it's like what ontology am I going to contemplate, and what are the implications of the ontology? So I sort of see ontology as transcending, any particular field of study. That we got to be clear on, what's our ontology. But so for me, it sort of seems to follow that, any physicist or person who sees themselves doing physics or creating physical theories that involves that kind of actualized single unique future, then they're kind of saying, to me, they're kind of having it both ways if they want to say they have live options. But that gets into this whole, compatibilism thing. That's a classic term in the free will, the philosophical debate around free will. And there are people who want to argue that free will is compatible with a deterministic ontology. And what they end up saying is that, well, what I mean by free will is something different. It just means no one's holding a gun to my head at the moment. But what it just goes back to person Genet. I think it was a philosopher Genet, and I can't remember his first name. He said, if what happened in the past is not up to us, and the laws that govern what happens are not up to us, then nothing that I do is up to me. Nothing that happens is up to us. And I think it's a consistent argument. So to me, you have to have an ontology that permits live options. And so that's what I feel we get from this sort of possibilist interpretation.
Yeah, because if each interaction has a realm of possibilities for its outcome, then you have not an infinite domain of options.
Right, like I can't just hover off of my seat right now if I want to. I don't have that free of will.
Yeah, I was going to say, you can become a painter, but you can't become a fish.
Right, yeah, there are definitely constraints on those possibilities. Yes.
But I think that, so the way that I look at it is that over a long enough period of time, with enough decisions made, then perhaps you can get closer to these things that seem really, really impossible at the moment. So, and that folds evolution into it, where I'm like, okay, you cannot become a fish. I cannot become a fish. But if I have a strong culture in my family where we spend all of our time in the water, and we develop our ability to fish, and we develop our ability to breathe underwater, technically natural selection says that there's no reason that we couldn't eventually evolve to become a marine animal of some kind. And that'll take a long time.
I like to think we started out as marine animals, but that's a different story.
I like that too. Trilobites were cute. I'm not sure they were probably something else.
Watery.
Have you heard of the?
Of course.
I'm sorry, complete tangent, but have you heard of the aquatic ape hypothesis for human evolution?
I have not.
Oh my God, it's so tantalizing. You have to check it out. There's a 2-part David Attenborough podcast from way back in the day where he explores this idea that the early ancestors of us, essentially, were shallow water monkeys, essentially, and that would explain everything from our bipedalism to, what is it called, vernix that's present in the fetus. All of this stuff. It's really, really fascinating.
That's so
anyways,
cool.
I just wanted, I couldn't pass the opportunity to.
I will look into that.
Oh. But that lines up perfectly. Like whether or not we started in the water or we started in the trees, it's like there's a series at the very moment. If you're a marine ape of some kind, you don't have the ability to leave the water. But eventually, through enough decisions made over enough time, that frame of possibility shifts enough that all of a sudden you have us talking on Zoom. And it seems impossible at the moment to conceive of it. And yet, that cannot be anything except for a series of decisions made within the space of possibility. Because somebody else ended up somewhere else, right? Like we had a common ancestor. Right. And those branches radiated. And how could it be anything
yeah.
except for the gradual shift of what's possible?
Yeah, absolutely. The possibilities themselves definitely change, and they are definitely, affected by what gets actualized. So it kind of goes to both ways. I've developed with a colleague basically a theory of transactional gravity that does accomplish, appears to accomplish what people have been trying to do, is just unify quantum theory with relativity. And it comes about based on transactions, basically, and that these actualize space-time events. But whenever you have and that's what a measurement is. So whenever you have this kind of actualization, it is bringing about specific changes in the states of the systems that participate in that transaction, and those in turn are going to affect what the level of possibility is like. So that provides a way to understand, exactly what you're talking about, where if certain choices are made among these possibilities to go in a certain direction, then that direction becomes more probable in the future. So yeah, it's a mutual thing.
I did read your paper this morning, by the way. I tried to, anyways. I did my best.
Oh, okay.
But it reminds me a bit of trying to understand the second law in terms of life forms, right? Because how in the world can a life form happen? And I think that the confusion comes down to not examining the entropy balance in total with the system in which the life form is existing. Because if you think about a being such as yourself or myself, it's probably most evident in toddlers or something, but we tear up the environment more than anything else in the universe, actually, per unit volume, right? Life is externalizing this entropy, about this chaos, let's say, at a very, very efficient rate. And so by examining the system in the context of the whole space enveloping it, then you get a little bit closer to understanding how you can have localized minima, but overall, this tendency towards, for lack of a better word, disorder.
Oh, yes. You definitely have to look at the total system, and not look at systems in isolation. It is certainly, we are dissipative systems, big time. And that's true. But it's still to me, the whole idea of creating order, is really an important issue. And I think this is where, you're concerned about physics kind of wanting to be the defining science of everything. Again, and others have argued to the contrary, like Robert Rosen. I don't know if you know him, but he was a biologist who argued that the life sciences, and in particular biology, was probably more fundamental than physics. And it doesn't necessarily have to be that way, but because, again, it goes back to what are our ontological commitments, what are our methodological commitments, and physics is very much wedded to that Cartesian notion of dead matter, pure extension, and thinking of it as dead. And then physics wants to construct everything in the world out of dead stuff. Mm-hmm. And then they have the hard problem of consciousness, which is like saying, I tried to make chicken soup out of rocks. That's the hard problem of chicken soup. It's like, just don't start with dead stuff, and death in, death out, right? So it could be that, I'm a physicist and I love physics, but again, it's your ontology. If you assume that the basis of everything is dead stuff, why do that? You don't have to do that. Nobody's holding a gun to your head.
Right. It's always shocked me that physics gets that king of the castle position, especially when it comes to things like astronomy, right? Which is funny. It's like we just make this weird ontological, epistemological choice that everything we see in the night sky should be explained in terms of dead stuff. I always found that to be a really strange just assumption at the heart of everything, because
it is.
Why? I'm not
because
saying
there's no function of will inside of physics, and the minute
right, but why
that
does physics get astronomy?
Well, because it's stuff. It's not, there's no evidence, right? So like you can go into this Thomas Goldian perspective where you start to redefine life as being something that is emergent from the organization of large scale structures, but nobody's really picked up Thomas Gold's torch. He's still viewed as being kind of, a big thinker and the proposer of massive ideas, but not somebody who had the mathematical bona fides that allowed him to actually go through and write some kind of equation that proved that the structure inside of planets or inside of stars can mirror the processes of life in any significant way. And so we operate by looking at the system outside of us as being exactly as we look at the rocks that are on our planet, which is just that, like,
but why don't we look at dolphins too, right? And ants and other things.
Yeah, but plenty of people are like, they're not conscious.
Well,
certainly not conscious like humans, right?
Yeah, so how do they see? That's the other thing. It's like, how does anyone know that a blade of grass isn't conscious? And this is the fundamental fallacy, because in fact, consciousness or awareness has no empirical correlate. I mean, no empirical, demonstration. It's sort of like you can't. There's this amazing story about a book called Ghost Boy, and it was written by a gentleman whose name escapes me at the moment, but he was afflicted by a terrible neurological disease at the age of 12 and was thought to be brain dead. So for years and years, he was in some sort of home and just lying there in a bed. And then at some point, and he was being shown Barney cartoons for like two decades.
God.
At some point, a nurse just kind of picked up on that, thought that there was something in his eyes, that maybe he was awake in there. And after a while, they figured out, and I think he was to slowly recover some just minute amount of being able to do something with his. He has frozen body. I forget what it's called.
Locked-in syndrome. The guy's name is
locked-in syndrome.
Martin Pistorius.
Thank you. Locked-in syndrome. So he had that, and they figured out that all this time he had been fully conscious, and he eventually partially recovered. Wrote this book. He's in a wheelchair and he has limited mobility, but. So this is the point, is that you can look at something and say, well, I don't see it talking to me and saying hi, so it must not be conscious, or I don't see it like being meaningful to my life in any way that I want, so therefore it's not conscious. And they were wrong, right? And so conversely, now we have stuff we call AI that looks like, hello, I'm your, and talks and acts like, it looks like us. Do we, and lots of people think that means it's conscious, but no, nobody knows. You don't know. You cannot know if anything besides yourself is conscious. You just can't. It's not an empirical matter, period. It's completely internal, private matter. And so, like, when people say, stuff like that, I'm like, well, you don't know that a blade of grass isn't conscious. So, yeah, it's just a weird human prejudice that if something doesn't look and act like me, therefore it doesn't have some inner trait that I have.
There's a really funny study that my mom just sent me, which was that a bunch of researchers at some university grew sunflowers and noticed that they do, so plants in general do this thing where they kind of turn over the course of the day. And they discovered that when you grow the sunflowers all together, that they will dance in such a way as to ensure that the plants they're growing next to have access to the sun. And so they're coordinating in order to ensure that it's not too crowded and that everyone in the community has access. Right, and it's like stuff like this.
For president.
I know.
Yeah, I actually have some sunflowers in my yard that are planted probably a little closer together than I should, and that they're just starting to bloom. So that would be neat.
Yeah, I bet if you put a camera on them,
it's just like really unsettling if you entertain the idea that the celestial bodies are doing what they want to be doing. It's like, what do you, like, how do you even nail down anything at that point? Now you're into behavioral science, which is just a complete no man's
Which
land.
doesn't even really work for humans, let alone stars.
Right, political science, social science, like this is every hard scientist's nightmare is trying to nail down what's actually happening in these complex living systems. And so it would be really nice if it was just atoms crashing into each other. That would really simplify our models quite a bit.
But I think that this is where statistics come in handy, right? Because we've been talking about the probabilistic nature of quantum physics. And I'm like, that works pretty well because it allows you to describe the system and say with some certainty that the system will behave according to these rules. And there was a moment where biology almost went in that direction. So at the turn of the century, before nucleic acids had been discovered, before they started to figure out that there was a true heritable material, they were basically like, well, look, you can do a genetic cross and you can do statistics on the traits that you see, and that's pretty much enough. And it was only through the efforts of the biochemists who were like, no, I think that there's something that you can see and inside of the cells that's actually doing the thing that's encoding something important. And by understanding that,
The genetic crystal.
yeah, the genetic crystal. And so, I mean, it's hilarious because the first guy who defined the nuclear material, they called it nucleon at the time, was collecting pus-filled bandages from a hospital, extracting the pus from them, taking those white blood cells, extracting the nuclei from them, and was able to determine that they contained some kind of massively enriched phosphorus compound. And he was like, I think that that's what's doing it. And then microscopy was also developing well enough that they could actually look inside of the cells and see that there was like this distinct region. And so the combination of biochemistry and microscopy led people to this place where they were like, okay, there's probably something there. But had it been small enough that we couldn't see it, I imagine that biology would just be happily continuing along its statistical path.
Genetic fields.
Yeah, like it just seems totally probable.
Yeah. Yeah. I mean, statistical descriptions are fine, but they're again, they're just sort of instrumental approaches. I mean, if you don't know where your statistics come from, then you're kind of not doing the whole job. It's not really an explanation, of what's there. Right?
And that's what it really comes down to, is that like how much of science is an obligation to explain versus how much of it is an obligation to describe in service of a future technological goal.
That's right, because engineering is all about descriptions, really, really accurate, predictable descriptions. But science seems to want something more than that.
Yeah, I mean, Einstein said, I want to know the mind of God, the rest is details. And, he disparaged some of the other stuff as the work of shopkeepers and engineers. And I'm like, well, I mean, I think engineering is marvelously creative. And I'm certainly not down on technology. I mean, we have to be careful with it. I think we have to be more careful than we have been. But yeah, I mean, I'm all for engineering, but it's just, there is this kind of thing about statistics. And I mean, what I like about the transactional approach is that it does at least give you a basis, some kind of conceptual ontological basis for this Born rule, the quantum probability rule, that yes, yields statistics, if you will, but we see them as coming out of something that happens in the world. We see, well, okay, it's not giving us a deterministic account, but it is at least showing the transactional approach gives you some kind of ontological basis for that rule, which before that was just a rule, was an ad hoc thing that Max Born kind of, said, your eyes start back and forth. Like what is this probability amplitude? Well, I get it's sort of a probability, but it doesn't have the right character because it's complex and probabilities are between 0 and 1. So maybe I need to take the magnitude of it. And he tried all these things, and no, magnitude isn't right because that wouldn't go from 0 to 1. Oh, you have to square it. Oh, if I square it, then I'll get a probability. And that's literally where the Born rule came from. Max Born just kind of just making a stab at stuff until he got something that had the right character. So that, that's not very, to me, that's kind of like you haven't quite finished the job yet. So, I mean, that's one thing I like about the transactional picture is it gives you a reason for that.
Are you depressed about the Clauser Nobel Prize because it signifies this mysterious interpretation as being crystallized in the mainstream?
Oh, kind of have to remind me, did he just recently win or?
Yeah, he won a couple years ago
I mean, the experiments were done 50 years ago, but he just picked up the medal.
For the
Bell's
EPR?
inequality stuff, yeah.
Well, not at all. I mean, it's kind of like he did some great physics work in explicating, the nature of these non-local processes. And experimentally, in kind of confirming it, yes, there really is this non-locality. So, I have nothing against that. I mean, where I tend to get a little discouraged sometimes is when physicists go into denial about the measurement problem of the conventional theory, and it's an interesting pathology there where there are different forms of it. There's like attitude of the measurement problem is here to stay. It is not in principle solvable. And I'm like, yeah, as long as you're working with your Yang only one-way fields, that is correct. But that since they assume that that's the only right way to do it, and then there are others who kind of just deny and hand wave around it and just kind of put their heads in the sand and pretend like it's not really a problem. And they go into instrumental mode where they get into these inconsistencies like the Frost-Sugar-Renner inconsistency, say, okay, well, quantum theory is just a tool for agents to get degrees of belief on things, rational agents, and they'll use it to, find out what they should see. And in this situation that I talked about before, where we've got the inner observer who predicts one thing, and then an outer observer who predicts something completely different, and they empirically have to conflict. They're different predictions for probabilities of outcomes. And then people will be, okay, so the inner observer will just kind of update his degree of belief. He'll find out he's wrong, and he'll just, do that. Yeah. And that's the story they tell themselves. And it doesn't really work because at the same time, they want to help themselves to saying that outcomes apply to inanimate objects also. So they kind of want to have it both ways. They want to say quantum theory is just an instrument that rational observers use. We can't define rational observer. Does a plant count as a rational observer? I don't know. So they can't define that, but they help themselves to that. And then they say, oh, but we don't want the outer observer to be dishonest and lie to the inner observer about what his outcome was. So we could say, have an automatic machine get an outcome and send it to the inner observer. And now I'm saying, wait a minute, you just used quantum theory to apply to a system, a physical system, not an observer. Which is it? So people talk themselves into these corners because they want to deny that there's anything wrong with the conventional theory in its ability to account for outcomes. And they say the most amazingly absurd things, and it's all kind of let slide, and people don't pick up on it because there's kind of a culture of averting your eyes from it. So we have that kind of pathology. That's my diagnosis, about.
Well, it's a philosophical problem, right? It's not necessarily a mathematical one, because the mathematics seem like they describe the systems relatively well. And the question then is, how do you interpret the results that you get? And that's not, that's philosophy, ultimately.
Well, actually, what I would say is they don't have all the physics right. That the math that they get has certain ad hoc features to it, like the Born rule. So yes, you're right, the math is right, but to what the math applies is left undefined, and you would get these problems about where does an outcome happen, at what stage in the process does an outcome happen, and that part of the theory, that inadequacy of the theory, is, I would argue, a deficiency in the physics theory, in that it doesn't have the right physical theory of fields. So once again, if you have your direct action theory that has a different physics and it ends up being empirically equivalent at the level of the probabilities, in other words, it yields the Born rule. So instead of having to help yourself to it, this theory, the direct action theory, gives you the Born rule. And it also explains for you at what stage am I going to really get an outcome where an observer, all observers would have to say, okay, yeah, an outcome really happened, like, at the Geiger counter in the box at some time. An outcome really happened. And then it's not correct to describe Schrodinger's cat as being in a quantum superposition. So it has wide ramifications, the inability to define what counts as a measurement and at what point in the process a measurement happened yields to like wrong physical descriptions, literally. So it's a subtle point because, again, a lot of the math kind of lines up. And then many times people will say, okay, well, you've got a different approach. Well, show me, give me a test that I can do that will distinguish your interpretation or approach from another one. And I mean, that's the thing, is that the probabilities that the transactional approach yields are the same as the conventional theory. It just corrects the anomaly, the measurement anomaly in the conventional theory. So in a strict sense, what we have is my theory is confirmed by experiment already, and your theory is refuted by experiment, right? Because the conventional theory is refuted by the fact that we don't ever see cats in superpositions, because it predicts that, So
I like that.
So that's the difference. That the theory is predicting absurd things, and the transactional approach remedies that, and it tells you, no, I'm sorry, your cat, we'll do a sleep or awake. Your cat is has a definite probability to be asleep or awake at any particular time, and you do not. It's not correct to describe this cat by a quantum superposition.
I wonder if to close down, you could make sure that people walk away understanding what you in particular are adding to this transactional idea, because we've talked to Carver, we've talked to Cramer, and you have a little bit of a different take, and I know we've been talking around it a lot throughout this conversation, but I want to make sure that you put that down concretely so that people can follow up on it and go and get into the details later. They can read your papers and your book.
Okay, sure. And while we were talking, it occurred to me I may have said something upside down about the entropic gravity, that gradient. The gradient by which the entropic force is increasing is actually because the area of the sphere that we're conceptualizing is in the denominator. I may have said it the other way around. Mm-hmm. But anyway, so as the denominator gets smaller, the overall quantity gets bigger. So that's the gradient that's getting bigger as far as the entropic force goes. So I just wanted to correct that in case I said it upside down.
There's probably very few people can do math in their heads while listening, so I'm sure it slipped by me.
I'm sort of sometimes. I always get things upside down. So anyway, so I think with both Carver Mead and John Cramer are still working with kind of a picture in which they think of space-time as kind of the background or container for everything physically real. And so that's one place where I've kind of diverged from John, and of course probably the mainstream in some sense. Although some physicists are now starting to consider the idea that space-time may be emergent from some fundamental level, which is nice. But of course, given our everyday experience, what we seem to see that we are in space-time, and that everything is in space-time, and it's kind of what we seem to see. But what I urge caution in the sense that people saw 300 years ago, they saw the sun going around the Earth, and it was obvious that the sun was going around the Earth. It's just as obvious that we live in a space-time container as that the sun is going around the Earth. So I try to kind of emphasize that appearances can be deceiving. and it was a big reshuffling mental, cognitive clash there to go, wait, oh my goodness, I don't feel like I'm moving, but I'm on a planet that's moving. So sometimes things at a bigger scale, in a bigger perspective, turn out to be different than what we thought. So anyway, the big to me stumbling block for progress is this idea that things are going on in space and time, so that for the transactional picture, we have literally stuff going forward in time and backwards in time, where you could like draw a space-time diagram and have these little zigzags and things. And that, I think, is a distortion. So, as I said before. So my innovation, if you will, is to say, with the transactional picture, let's be really face up to the fact that these quantum states are Hilbert space objects. They're complex and multidimensional. The states that these entities are described by are not things that fit into space and time. So let's stop trying to pretend that they do, and just say there's a domain, that is somehow mapped by Hilbert space. And I don't pretend to know, much about it. If anything, I symbolize it by the submerged iceberg portion. And so that's kind of been my main development in terms of ontology. What I've also done with the relativistic development is to really elaborate the relativistic quantum direct action theory, because there are some long-standing confusions about what the absorber theory or the direct action theory is. On the classical level, it is really very different than it is at the quantum level. So what Feynman and Wheeler and Feynman and so on were working with was a situation in which they assumed that all charges, all of these field sources, are always responding, that there's always absorber response, that it's universal. And this is not the case at the quantum level. So what happens at the quantum level and at the fully relativistic description, which doesn't have any limits on energy and speed and so on, and mass, what's really happening there is that there are amplitudes for an offer wave or a confirmation wave to be emitted, to be generated. And so these are very much in play, and offers and confirmations are not universally created. They happen under certain specific circumstances. And the basic, the basic amplitude is literally the charge, the unit charge, so that the charge of the electron, the charge of the proton, that's actually the amplitude for this entity to generate either an offer wave or a confirmation wave. And so that was my, innovation, if you will, that kind of links the non-relativistic transactional formalism to the fully relativistic level. And it allows you to say, it allows you to further give more detail about the circumstances for emission and absorption and so on, and how they happen. And it's not deterministic, but it remedies, people kind of thought, some people would say, oh, you're just using absorber as a placeholder for observer. And you're not really defining what is an absorber, and this does that. It says it's simply a charged, it's a field source. And when the field sources are not, generating these offers and confirmations, they are still in contact with what's called the Coulomb force. So they still have this electric field kind of force between them, if you will. So they always have this force. And so what that does is allow us to clearly distinguish between force and energy. So this connection that is kind of more primal than the offers and the confirmations at the relativistic level is just it's just a force. It's not force acting over a distance. So it's not energy. Whereas energy is the photon, the actual on-shell, so that's the technical term, but the offers and confirmations, they give you a radiative process, which is real energy. So that distinguishes an energetic interaction from a simple force interaction. And that really gives you a lot too, because it allows you to kind of make defang, if you will, the infinities that come up in standard quantum field theory, because in a sense, a charge is always interacting with itself, and that's just a Coulomb force. So in the transactional picture, it's not energy. That's often called, self-energy. Oh my God, the self-energy is infinite. It's blowing up. This is crazy. Oh, now we have to do renormalization. And this is so embarrassing because we've got this infinite energy and we have to throw it away, which is what Dirac said. But you're not doing that. It's kind of an infinite self-force.
It's like a possibility.
Exactly. Yeah, it forces at the level of possibility. And so it can be, and maybe it isn't even infinite because there may be a discreteness going on here, but very huge amounts of self-action, but they aren't energy. And in the standard way of, the bucket brigade quantum field theory picture, it has to be considered energy. So the standard theory can't distinguish in a principled way between these real photons that are radiated and really energy and these so-called virtual photons that are just the force. And it has a hard time accounting for that. So this approach just kind of offers a lot in the way of kind of explaining a lot of things that are puzzling in the conventional approach.
I know I said that was going to be my last question, but one last tiny little question. Speaking of interpretations, do you have an interpretation of what charge means about what an atom is actually doing?
Yeah, charge is just its tendency to emit or to not emit. Its tendency to absorb. It's a propensity. And in a very specific sense, that's all it is. It's the coupling constant. And even Feynman said that in a sense. He said a charge is the probability that a field source will emit a photon. And he was half right. It's also the probability amplitude that a source will absorb a field photon. But see, again, missing yin in the standard approach. Nobody thinks absorption reception is worth anything, even though it's crucial.
Interesting.
Well, it's half the
so
picture.
What I'm working on going forward, exactly. And what's not understood is that you get nothing without it. You get nothing. So what I'm working on going forward is actually probably another book project where I'm going to, lay this out and just talk about how physics has so many maladies because it's just missing yin. It doesn't see yin.
That's wonderful.
That's really cool. So, by the way, what's the name of your book so people can find it if they want to check it out?
Well, actually, during the break, I brought up 3 of them. So this is
cool.
one, Understanding Our Unseen Reality is the one I wrote in 2015. It's for the layperson.
I love that picture on the cover, by the way.
Pictures. Yeah, this is a fun one, isn't it? Yeah. So that has just really conceptual presentation, and it doesn't have any math. And you don't need any math because you just have little symbols, and that's all these quantum states are. They're little symbols that, And then this is the follow-up to that. It's called Adventures in Quantum Land. And this gets into a little more detail about the philosophical ramifications of that whole, transactional picture. And then this is my latest. It's the second edition of my book with Cambridge University Press, where I try to give a more comprehensive, quantitative presentation of the theory. And this deals with the recent developments in terms of the relativistic aspects of it.
Very cool. And then if people want to reach out to you, do you do any social media or anything like that? Or you have a website that people can reference?
I have a blog. It's just transactionalinterpretation.org. And then I have an author page, so it's just my name.org. So ruthekastner.org.
All right.
And I'm on Facebook, and most of my ranting is done on Twitter, most of my political ranting. So
excellent.
So you can hang out with Nastia over there. I've never touched Twitter in my life, so I'm trying to keep it that way.
You're smart. I'm trying to just be done with that.
I totally understand that. But I want to say thank you for taking the time to walk us through all this and to give us a good handle on your ideas and help us understand the landscape better than we did before we started.
Well, you're so welcome, and I really appreciate the invitation, and you guys are really fun to talk to, so it's always fun.
Thank you so much.
And I really hope that the next generation picks up these ideas. Looking at at you and Cramer and Carver. I'm really waiting for the next person to pop out of the woodwork and just run with these things. Because
Like
I think,
early career postdoc.
yeah, I'd love to meet that. If anybody knows who that is, please send me an email because I really want to see the next generation.
Well, I would
running
welcome
with
that.
these.
I mean, I do have a little entrepreneurial thing that I started called the Quantum Institute. And I have a little website, theqinstitute.org. It's in its early stages. Don't really have any significant funding at this time, but it's what the idea is. It's a transactional think tank. People can, get a hold of me through that, and I need to update it a little bit, but that's where, any new stuff will be posted, and where maybe I'll get my postdoc who wants to study this. But
I mean, please stay in touch if you do. I would love to see more people working on this. So let me know if there's any developments. It would be great to find out about that. But yeah, otherwise, thank you so much. This has been awesome. I really enjoyed talking to you today.
Thank you. It's a pleasure.
All right. Take care. Have a great rest of your day.